Today, so far, we have analyzed, we have been discussing the case of continuous variables. Like for instance, in the child data, you had looked at the mean temperature variables like the mean temperature, percentage of children who are stunted. So these are, by their very nature, these are continuous. However, variables can also be categorical. For instance, we may be looking at the political structure. So what is the ruling party in the state? So we can have BJP, we can have Congress, and we can have a regional party. There are three options, and we label them 1, 2, and 3. So depending on who has won the election, a state will be given the value of 1, 2, or 3. A binary variable is whether there has been flooding in the district. So if there has been flooding, the district is assigned the value of 1. And if there hasn't been any flooding, it is assigned a value of 0. Now, the important thing to note is, so these are called categorical variables. Now, the important thing to note is, so I'll just close the window. That although we are assigning numbers to the different categories, the numbers do not mean anything. There's no order. Like for instance, if you say that 70% of children are stunted, it means that if you take 100 children, 70 of them will be stunted. If we go to another district with a higher value, it means that district has a higher stunting level. So for continuous variables, numbers have a meaning. But for categorical variables, numbers don't really have any connotation. There is no order. 2 doesn't mean that 2 is not necessary. It's just a descriptive label. It doesn't mean that you have a greater value. So we can easily change the labels. For instance, in the flood case, we could also have labeled it as 0 if there has been flood, 1 if there hasn't been any flooding. In the political example, we could have labeled them BJP 1, Congress 2, regional parties 3. We could also have labeled regional parties as 1, and so Congress as 2 and BJP as 1. So we can change the order. It doesn't lead to any, it doesn't make any difference in results. So what we are going to do today is discuss, first we are going to discuss categorical variables. We are going to discuss maps which will show us how to examine the regional distribution of categorical variables. So there are 3 types of maps. Unique value maps. This is basically univariate analysis. They can be extended to co-location maps, which is an extension to bivariate analysis. And finally, micromaps, where we look at the interaction between conditioning variables and another variable, a third variable, which is our interest. I'll explain all these later on. This is basically the extension of unique value maps to a multivariate context. So unique value maps apply to a univariate situation. We are looking at one variable. Co-location, this is the bivariate map. We are looking at two variables. And in micro maps, we look at three variables. So micro maps are also called conditioning maps. Okay. So there's not much theory behind it. It's mainly, the first part will be mainly maps. So the first data set that we are going to use is the NYC data set. So we create a box map for the variable kids 2000. And if we right click, we can save these 6 categories. So save categories, I name them for convenience. KitKat. I click on OK. And you can see that a category has been created 4, 3, 4 like this, depending on which of the areas it lies. So I've got an extra variable. Let me first delete that. Then I go to map. So the variable kids 2000 is the number of kids, average number of kids in families which are located in a particular ward. So this is obviously continuous, but we have converted this into a discrete variable with 6 values. So 1 implies lower outlier and upper outlier is given by 6. But be careful that we don't have, if you look at this map carefully, let me expand this. The upper outlier doesn't have any observation. So although we have 6 categories, we actually have only 5 categories. So let me keep this. And I want to create a unique value map. So again, I go to map, and if I come down, here it is, unique values map. So I click on KitKat. So you can see over here that there are no deep reds. That is why instead of 6 categories, we have only 5 categories over here. The blue lower outlier has 3 observations. Over here, we have got 3 observations. This is 11. This is also 11. The last one, deep pink, orange, is 14. Here also we have 14. Okay, so we can see that it's very clear that the 2 maps are coinciding. Now, I'll just show you one thing. that if I click on this, I can drag it. Okay. Let me show this again. So I'm clicking on this category over the numbers and keeping the mouse down, I'm dragging it. Yeah. So you can see that 14 was actually category 1, 2, 3, 4. But we have, by clicking and dragging, we have made it, we have changed the color. It is a light blue. So categories can be changed. The reason that I'm showing it to you is that when we are considering categorical variables, and as I've said, the labels don't mean anything. 1, 2, 3, 4, these are just labels. I could easily have named them A, B, C, D like this. So it's possible to change the labels just by clicking and dragging. But I don't want to do it. I want to keep the original label. So I just create the map again. Unique value, KitKat. Okay. Then, so this is how we create unique values map. And as you can see, I'm just focusing on one variable. Now let us go to the co-location maps. In a co-location map, what I'm doing is, first I go to map, I create a box map, and now I'm taking a variable called pub_ast00. So this is the percentage of children who have received health services in the public sector. So you can see that this is the distribution over here. And, so again, what I do is I create the categories. So, PubCat. And again, I create a unique value map. Oh, sorry. My Geoda just crashed. So just do everything again. Please bear with me. Box map. KitKat. Box map, where is pub_ast? This. PubCat. Then the unique value map. Okay. So these are the 4 maps that we have. Now, in order to create a unique co-location map, I click on them and I have to select 2 variables, KitKat and PubCat, and one change over here. It is based on a box map, so I mean change the color scheme to a box map. So what we can see is we have got 4 categories for the public cat, PubCat, and 5 categories for KitKat. So what we want to see is over here, let me start from here, co-location. It means that this blue means both the variables lies in the same category. So for instance, this is category 2, and over here, this is also category 2. Look at this. I hope it's visible to you. Look at this region. So this lies in, it indicates 2. The value is 2. So this will be over here, light blue, but that is because there's no 1 over here. So we start from 2. Here also, if you look at, it's deep blue, but this is the color, deep blue is the color for category 2. So what the co-location map does is, it goes to a district. So let's say this one. Then it says that, look, we can have 2 possibilities. One is, in both the maps, unique value maps, the district has the same value, 1, 2, 3, whatever. If it has the same value, let us say in both cases, the value is 2, then this is labeled as 2. If this district has a value of 4 for both variables, it is labeled as 4. But if there is a mismatch, the value is 3 for one variable, it is 2 for another variable, then it is lumped as in the others category. So we have an overlap for these 4 categories. We don't have an overlap for the others category. So we don't have an overlap for these, but the bright ones you can see, we have overlaps. Overlaps in number of families, the number of kids, and whether the family seeks public assistance. So what we are getting is, in these districts, the interpretation is that if you have large size families, the number of kids, number of children is very large, we would expect that this is a family which is socially and economically vulnerable. New York, it possibly means Black population, possibly Hispanic, migrants. So areas which are mainly dominated, which are populated by Black population or those who are economically poor, they are more likely to seek public assistance, public health services. So this is, co-location map shows the overlay. You have already looked at the multivariate gearing. If you remember, MD has discussed this. So this is some sort of a multivariate gearing. The difference is we are doing the analysis for a category, for 2 categorical variables. Okay. So is this clear, everyone? Is there any point which you would like me to repeat? Let me close these maps, but I'm still going to use the NYC dataset. Uh, the third type of map that I'm going to show is called micromap. So this is not necessarily uh, connected with working with discrete variables, but what I mean, the equivalent is a table like this. As I've told you that that spatial statistics is basically the conventional statistics, but we are adding location to it. So let us suppose that we want to create a table like this. Uh, so it's the size. So I've got, so using two categorical variables, I've divided the sample into 4 groups. So this one is a rural area, which is also flood prone. This is a rural area, which is arid. And these are urban areas, which are flood prone and arid. So let us suppose we want to see whether we want our variable of interest is, let us suppose, is the mean income. So what are, in each of the cells, we have the mean income. So this one is the average income for all households who live in rural areas, which are also flood prone. This one is the average income for households residing in rural areas, but which are not flood prone, which are arid zones. And this is for urban areas. So in micromaps, we are basically extending this type of table to the spatial statistics. So micromaps are also called conditional maps. So I'm clicking on this. So this is the horizontal cells. And so for horizontal cells, I'm clicking on for his 08. So this is the percentage of immigrants from Spain. New York is a Hispanic population. And over here, I'm looking at the rent. This is the rent in 2008. So I'm clicking on. No, sorry, this should be household size, HH size. See where it is. HH size 08. And the variable of interest is rent, 2008. So what I'm trying to do is the horizontal cells on one side, we have the percentage of Hispanic families. On the other side, we have the family size, and we want to see the relation between whether areas with high proportion of Hispanic families and with large family sizes, whether they reside in high rent area, whether it drags down rent or whether the rent goes up. That is what we want to see. So we see that we have got the default category is 3 into 3, and it's not very meaningful. So I'll show you how to correct this later on, but let me first explain what the graph means. So this is basically, as you can see from the left-hand side, it is basically a box map. And the high outliers, low outliers, all these are shown. So all the 55 districts will fall in either of these 9 maps, but it will appear only once. Okay, now how do we draw the maps? So over here, this is the household size. So what we have done is over here, this first block. So these are household size. We have used 2 cutoff points. So we have looked at all districts where the household size is below 2.307. So these 3 districts. The second line is, the middle line is where the household size lies between 2.30 to 2.588. And the topmost line is all districts where the household size is above 2.5. Similarly, on the horizontal axis, the percentage of Hispanic population has been used to divide the districts into 3 categories. So the first column, the percentage is below 31.9. Second column, it lies between 31 to 42. And third is, it lies above 42. So we have a 3 into 3 cell. So this is basically a table. And in each cell, we put in the average rent. We plot the box map for districts in this cell. So out of the 55 districts, only some of them will lie in each of the cells. And what we do is we draw a box map for the districts in that particular cell. So for instance, this cell, low percentage of Hispanic population, but large family size. 1, 2, 3, 4. We have got 4 wards like this. Okay, so is this clear? Then I'll show you how to interpret this. So you can see that if you go to horizontal bin breaks, quantile, it has been, we have formed 3 categories. Let us make it 2. So now this is a 3 into 2 categories. Let us reduce the vertical bin size. We make this 2 again. Okay, so depending on your sample size, like over here, we have only 55 districts. You have to decide on the number of bins. So for instance, if you have a very large NAT regimes data, you have 3,000 observations. In that case, you can increase the number of bits. You can make it a 5 into 5, something like that. Now, let us look into the interpretation. Look at the diagonal part. Remember, the light blues are the low rental, and the deep reds are the high rental areas. So what we can see is that, let us look at the first row and compare it with the second row. What we can see is if you have large family sizes, this is the first row. What is the color of the districts? They are mostly light blue and some of them pink. If we come to smaller families, that is the second row, we can see that now we have red and orange. Red is upper outlier and orange is above Q3. So it's between the third quantile and the upper fence. So you can see that there's a clear relation between family size and the rental value of the area. If the family size is smaller, the rental value comes down. But if the family size is larger, then these larger families drags down your rent. So is it clear, everyone? I'll then come to the Hispanic effect of Hispanic population.
রিলেশনটা একবার বলবেন?
হ্যাঁ বলছি। Look at what is the difference between the first row and the second row. The second row, see the division is this, household size, and the cutoff is 2.4. So all districts who are below, who have small families, the family size is below 2.4, lies in the second row. On the other hand, families who are larger, above 2.4, lies in the first row. Now, if you compare the first and second row, you will see that the first row, both the cells, this one and this one, are light blue or light pink. So that means if the family size is above 2.4, remember the color denotes the rental area. Okay, the average rent in that borough. So what we are seeing is if the family size is large, then the rent is also low. So large family sizes pulls down rent. On the other hand, if you come to the second row, the bottom row, so in these districts, family size is small. So you can see that the rental value is high. Some of the districts are deep red, some of them are deep orange. Okay, you do have an outline, this one for instance, over here, but by and large, look at them. Most of them are orange, deep orange or red. We also have some light oranges or pinks also. So in other words, the micromap reveals that family size has an impact on the rental value in New York City. Now, what about the other variable that we have taken? The percentage of Hispanic population. So again, we have formed two categories. The first column is you have a low proportion of Hispanic population. In the second column, you have a high proportion of Hispanic population. So now if you compare vertically, you can see that, look, both of them, I mean, do you have any distribution? You don't have any clear-cut picture like this. If you look at, if you cut it vertically, you have deep rates over here, but you also have high values over here. You have low values over here, low values over here. So that means whether a borough is inhabited by Hispanic or migrant population doesn't determine the rental value of flats. It is mainly the household size which determines or influences the housing fact, the rental value. Okay, is it clear, everyone? So in micromap, what you should do is you should try to remember, keep in mind the sample size and form the categories accordingly. So if the sample size is below 100, make it into 2 into 2. Below 100, 150. But if it is something like 30,000, 40,000, then you can increase, you should increase the size. Now, unfortunately, I can't show it, but suppose we have a situation when all this is light and this is deep red. Okay. And you have mixed patterns over here. That would imply that areas which have, no, sorry, what we would like is over like this. We would like it over here. Yeah. So if we compare it diagonally, what we can see is if the percentage of Hispanic people are low, family size is low, rent is high. But if the household size and Hispanic population increases, then rental value comes down. But we also see that there's a large proportion over here, high values. So our conclusion would be that only the household size determines rent, not the composition of the population. Okay. So what you can do is you can try it for some other variables also and see what happens and try to interpret it. For instance, conditional maps. Let us look at public assistance. So this would imply that the family is poor, household size in 2000, and rent also we make it. Yes, I think someone has a query. Rent, unfortunately, we don't have for 2000, but let us make it 2002. So let me reduce the bins. One time I make it 2 horizontal I make it 2 and I expand it. So we can see that if the family, if there's a reliance on public assistance, the rent comes down. If the households don't rely on public assistance, no, we don't get a very clear picture because this is the same. But if you compare between household size, yeah, the bottom, small family size, these are high rental areas. Small family size, high rental, and these are large families, the rental value comes down. So we can see that in New York City, the family size determines the rental value. Okay. Then we come to clustering of categorical maps. So what we're trying to do over here is, just as we had the Lisa or Jettis odd, we are trying to identify clusters. Now, if it was a continuous variable, clustering would be, identifying clusters would be very easy. And we could simply just use the Anselin's Lisa local indicators, or we could use the Jettis odd, Geary, whatever. But in case of categorical variables, we use a different type of tools. One is called the local, sorry, there's a typo over here, local join count. And this local join count can be either univariate, we are focusing on one variable, or we can take two variables. And this can be extended to what is known as Lisa quantile maps. Specifically, what we are going to do is, we are going to look at binary variables. So multiple categories, just a categorical variable cannot be analyzed using this join statistics. We have to look at binary, we have to reclassify them into a binary group. So we apply the Lisa principle to estimate or map using the univariate local join statistic, and then it is extended to a multivariate context. So we are going to use two data sets for this, both on Chicago. So we are shifting from New York to Chicago. Chicago Common Pop, which you already have, I've shared with you. So this contains population and change in population for 2000 and 2010. I'm not sure whether we have the data or not, because I think we illustrated merging with this. And the second data set is Chicago Health, which contains health and socio-economic indicators. Now, any type of clustering implies that we have to use the concept of neighborhood, a contiguity. So we have to create spatial weights. And for our purpose, we are going to use Quine's contiguity in both cases. Okay. Now, particularly the univariate local join statistics is maybe a bit complex for some of you. So don't worry if you don't understand, particularly those who are coming from undergrad may find it difficult. But the others also may find it a bit not so easy. But I'll try to give an example which hopefully should make it clear. So as I've said, we have a binary variable which is coded as 0 and 1. So a particular area will have either a value of 0 or a value of 1. Now let us look at its neighbor. So there are three possibilities. One is that the value is 1. So the first district, what we call I, has a value of 1. And the second district also has a value of 1. We call it black black or BB. The another possibility is that district I has a value of 1, but the neighboring district has a value of 0. So this is called B down. And the third category is that you have 0. It's 0, 0. So we call this white. So BB and WW are cases of positive spatial autocorrelation. So these are the first two groups. Yes, please. So over here, the district I and its neighbors J both have similar values. That is why we call it positive spatial autocorrelation. And in the second case, this one, district I has a particular value, the neighbor J has another value. So this is a situation of negative spatial autocorrelation. Now, coding here, so far what I've said is the coding is not very important. I could code it as 1001. It would not make any difference. Here, however, the coding has to be done very carefully. You have to code. So since it's a binary variable, the variable x can take two values. You have to code it in such a manner that one has a lower probability of occurring. In other words, the frequency of regions taking the value of 1 should be less than half. Why is it important? Let me explain this carefully with an example. What is a binary variable? An example of a binary variable is gender. Suppose we are looking at the seating arrangement of students in a classroom. So you have two types of students, boys and girls. What is clustering? When would we say that there is clustering? Clustering would be that boys are sitting together, girls are also sitting together. There may be some boys who are sitting with girls or vice versa, but a cluster is 6-7 boys are sitting together. A girl cluster is we have 10-12 girls who are sitting together. Okay. So is the meaning of a cluster clear? Okay. Now, why are we why are we coding in the way that I suggested? If the frequency is low, it should be coded as 1. See, what we are trying to do, suppose we have a class in which there are 100 students and 90 of them are boys. Suppose we randomly, we assign the seats randomly. Okay. Will we still have clusters in this situation? I want an answer for this, by the way. So someone has to unmute. But are you understanding? Will I explain again?
Sir, can you please repeat the question once?
What I'm saying is that you have a class of 100 students and there are 90 students who are boys and 10 students who are girls. Now you arrange the seating randomly. Okay. Will the boys cluster together?
প্রবাবিলিটিটা বয়েজদের জন্য বেশি।
Exactly. Why? Because they're 90. I mean, you will have to sit besides another boy. On the other hand, so even if we go for random assignment, the formation of clusters will be very high in this case. If you look at, try to identify clusters of boys. But look at the cluster for girls. If we assign them seats randomly, will you have clusters? Remember, there are only 10 girls. So you're randomly seating them. It's very unlikely that they are going to sit all together. Cluster is they are sitting all together. Now, if you see that all of them are really sitting together, or let us say 4 girls are sitting together, then that would be something which is unexpected. It implies that you have moved away from random assignment. There is some process, some force going on, which has resulted in the girls forming a cluster. Is this clear? What I'm trying to say is that you have the population is divided into 2 groups, mutually exclusive groups. We should not look at clusters for the numerically dominant groups. So boys are numerically dominant, 90% are boys. Even if you go for random assignment, you're still going to have boys are going to sit together. Okay. So it's impossible to determine whether they are sitting because they want to or because they are sitting randomly. On the other hand, if you see that the girls are all sitting together, is it random? It's more likely that the girls have decided for some reason to sit together. So in other words, there is some process inside the classroom which has resulted in a cluster of girls sitting together. The next task will be to identify why the cluster has formed, but this is the task of spatial regressions. So I'm not going into that. What the BB joint does is it tries to find out whether there are clusters of girls. How do we do it? So we move to a particular seat. We go to the first desk. And if there's a boy sitting, we drop it. We go to the next seat. Again, we have a boy. So we move to the third seat. This one is a girl. So xi is equal to 1. Then I look at the neighborhood. So then I look at the neighborhood and I see that, and I count how many of the neighbors are also girls. Okay. Then I move to the fourth seat. If it's a boy, again I drop it. If it's a girl, again I count how many of them are girls. How many of the neighbors are girls. So what I'm doing is, these are all seats in a classroom. And I've just shown this. Okay, so I'm starting from here. So the yellows are the girls. Okay, so this is a boy. If it's a boy, I'm dropping it. I come over here. This is also a boy, so I'm dropping it. And in this way, I come to this one. This is a girl. Now, how many neighbors does this girl have? 1, 2, 3, 4, 5. But how many of them out of these 5 neighbors are girls? 2 of them are girls. Okay, so the join is 2 over here. This is a boy, I drop it, I come over here. How many are girls? Of the neighbors are girls? Only 1. So similarly, I come down. Let's say I come over here. And now out of the 3, 4, 5, 6, 7, 8, out of the 8 possible neighbors, 1, 2, 3, 4, 5. 5 of them are girls. So do you understand how this statistic is calculated? Jishnu?
Yes, sir, understood.
Okay. Now, then what we have to do is, so we get a number. Okay. We get a number that, okay, this is the statistic. So what we do is we count it for these people. I've got 2. Here I've got 3. Then for this person, I've got another 4. Let us say I get a total count of, let us say 50. Then I have to again reshuffle, permutate, just as in the answering. These are indicators, and find out whether the number that I'm getting is 14, whether this is higher than the average number of joins. Okay, so what I do is, how many girls do I have? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I take these 11 and I start randomly assigning them. Okay, and I find out how many joins. And I do this repeatedly. So I've got, let us say, 99 permutations, and I find out what is the average join. So this is the average join for random assignments, and I look at how many joins I got in the original data. So I look at the distribution, and then I can conclude whether the number of joins that I've got is statistically significant or not. So over here, we have got, this is the statistics, we have got 2 points, xi and xj. So these are same values. We take any variable, so we can take rent, but rent is of course continuous. So we have to convert rent into a binary variable. So let us say that we take, we have got a binary variable, and we look at xi is the value of this binary variable at point I, and xj is around the neighbors. And the spatial matrix is given by wij. So a join is counted when we have a BB situation. Both I and the neighbors j are 1. Okay, if we don't have BB, then at least one of them will be 0. Either xi will be 0 or xj will be 0. So BB indicates both xi and xj are 0. So if any of one of them is 0, then the join will become, value of join will become 0. So when x I equal to 1, it corresponds to the sum of neighbors for which the value xi equal to 1 holds. So, any questions up to this point? Achha. Now, will I show this map or will I go to the second concept, the bivariate join count statistic? Which one will I do?
The map.
Yes, please show the map.
Okay. So the data set over here is so the data set over here is Chicago Common Pop. So I had shared this on the first day. So I open this. So let me have a look at the population. So you can see that I've got a variable called pop plus. Pop plus is if population increases, then this is 1. This is 0. And if the population decreases, it is numbered as 1. So let me first do a unique value map. So this is a unique value map, and you can see that pop plus has 2 values. So the light blues are the boroughs or wards where population has decreased. Population has decreased, and 1 is where the population has increased. So you have to now go to space, and if you come down just below the jetty sort, you see there's a univariate local joint count. Sorry, I forgot to load the weights. So I'll either have to create it Let me see if it is created. No, we don't have it. So let us see what will be the variable. So NID will be the unique ID. So we create weight manager, we create, this is NID, and we choose queen contiguity, order of contiguity 1. We just save the weight file. So I don't really need the weight file anymore. So the first thing that we should do is create a weight file. Then I go to space, univariate local join. I choose pop plus, and you can see that the weight has been automatically loaded over here. So this is randomization, 999 permutations, and we can see that there are only 3 areas where we have clusters. So these areas are wards where the population has increased, and simultaneously in the surrounding areas also the population has gone up. So you can see over here, this is 1. So if you come to the unique value map, just let me see over here whether, yeah. So you can click on any of the maps. There's right click, there's a connectivity, and show selection and neighbors. So I'm clicking on this. Sorry, I should click on this, and you can see that the neighbors are identified. So over here, for instance, this one, this district, we can see the neighbors. The district I is indicated by the red line, and the surrounding areas, we just increase the size. And the neighbors are indicated by the red. So you can see that out of the neighbors, this one, the bottom one, has a similar characteristic. So we don't really have clustering over here. I mean, they may be, you can see that they are clusters, but this has mainly happened randomly. Once we test for statistical significance, clustering has occurred only in 3 units. These 3. Okay, so this is again a test of the statistical significance. So the important thing is we could also have done it for pop pop negative, but it won't really make sense. Unique values. See, I mean, there are 60 areas where population has come down. So I mean, it's not very meaningful to look at clusters over here, but I'm just doing it for the heck of it. And you can see that, well, it looks to be covered with clusters, but the significant clusters, very few. So as I've said, that this is what I'm doing today is a Anselin map or Jetty sort map, the local indicators. We are trying to identify clusters, but unlike the clusters that MD discussed, we are not using a continuous variable, we are using a binary variable. The analysis that we had done used only one variable. We simply looked at whether population increased or decreased. This is a binary case. We can also combine two variables. So xi and zi. Okay. But both of them has to be binary. So x takes a value of either 0 or 1 and z takes a value of either 0 and 1. So we can distinguish between two situations. One is co-location and the other is no co-location. Now, what is co-location? Co-location occurs when it's possible for both the variables to take the same value at a location. So in other words, if you choose a particular ward, a borough or district, it is possible to have xi equal to zi equal to 1. For instance, let us take two variables. One is whether the district is a rural district or urban district, and two is whether it is arid or non-arid. So let us say that urban is 1 and aridity is 1. So it's possible for a district to be both urban and arid. This is a case of co-location. Okay, so it's not the characteristics are not non-exclusive. I mean, another example, the rental value is high and the density in a particular ward is also high. That this is possible, you can happen. So an area can have high rent, the density can also be very high. So a particular region has values, x is also equal to 1, y is also, z is also equal to 1. Now, what is no co-location? No co-location is that whenever xi is equal to 1, then the other variable z is not equal to 0. So just yeah. This happens when the variables are x and z are mutually exclusive. So in other words, if we consider pop plus and another variable pop negative, if a district has the population grows in a district, the growth rate is positive, we cannot have pop negative equal to 1. Because pop negative equal to 1 implies that your population has actually gone down. Okay. So, no co-location is used to assess what we call negative spatial autocorrelation. So, what we want to see is that you have an area. Okay, I'll come to that later. Note that in this case, the incidence of Zi should be low. So we have to frame X and Z accordingly and also put the values accordingly. X can be anything, but Zi equal to 1 should be low. Otherwise, cluster formation is natural. So now the statistic is given by BGC is equal to this one, and the conditioning of no location ensures that 1 minus zi is equal to 0 whenever x equal to 1 and vice versa. So in that case, the statistic simplifies to the one given at the bottom, xi summation wij into jz. So whenever xi equal to 1, the second line, the second formula, the first formula simplifies to the second formula. So what we have is, it is a situation when a district has a value popnik equal to 1 and it is surrounded by districts for whom pop plus equal to 1. This is somewhat more complicated. So I don't need this data. We have to open the data which I sent you today, which is the Chicago health table. So it is COM area. So this is again Chicago, but the health indicators are different. So we are going to look at two variables, one of which is poverty and the other is death due to diabetes. So first let us create the weight matrix. Let me see whether we have a weight matrix over here. No, we don't have it. So we have to create it. So create from area ID. So the weight file has been loaded. So the first thing that we do is create a quantile map with four categories. And let me find out diabetes. Yeah. This is diabetes A, mortality due to diabetes. So you can see that we have got high areas. These are the high incidence. There's a huge cluster over here, another cluster over here. So mortality due to diabetes is, there's a very strong level of apparent cluster. Because remember, we have to do the statistical tests. Okay. Now, what we do is, we have to, this is a continuous variable. So what we have to do is to use this map and form a binary category. So I right click and I save the category. So dcat, calling it dcat. I'm clicking OK. So you can see that a dcat has been created, but you can see that values are 4, then you have got 3, then 1. Over here we have got 2. So it's not a binary variable. We cannot calculate the joint statistic using this one. So what we have to do is, we have to club the first 3 quantiles, 1, 2, and 3, and make it 0. And the fourth quantile should be classified as 1. Now, how do we do it? Any idea? Very often you will want to create a binary category, as you will see in the next class. When we go for spatial regimes, you will need a binary category. A continuous variable has to be classified into binary. So how can you do it?
So we have to classify a continuous variable into binary.
Yes. What we have done over here, we have got 4 categories.
Yes, sir.
Okay. So we want the first 3 categories, first 3 quartiles should be coded as 0, and the fourth, the topmost, as 1.
So I guess we can code it by, like, if it is within a certain range, then that is 1, and if it is not falling within that range, then it
Of
is
course,
0.
that is what we have to do. It's very easy to do it in Stata. How will you do it in Geoda?
No idea. So,
So you go to table, selection tool, and assign values to currently selected. Okay. So over here, dcat, and you make this 4. So that means you are selecting the last quartile, while the first 3 are not selected. So you select them. So over here, you create a target variable. So this is another variable that you have to create. Let me call it sdiab. We add it, and you can see over here that if it is selected, the value of 1 is assigned. If it is not selected, 0. Then I apply this, and you get a message: values assigned to target field successful. So let me deselect it and go to tables. And you can see over here, the first 3 are 1, then I've got 3 zeros. So let me see. The first 3 were 4s. So these are 1. Then we have got a 3, 1, 1. Then again a 4. So the first 3 should be 1, then 3 zeros, then again 1. Let's see whether we have got that. Yes, that is exactly what we have got. So you can create binary variables in 2 steps. First is to create a quantile, and then, or not even quantile, you could directly have done it in some cases. Then get this. So this is one, and second. Sorry, was there any question? You have to do the same thing for another variable, which is poverty. So we want to, basically we want to see whether poverty is responsible for high mortality from diabetes. So the variable is POV50P. So we get this again quartile, and if you just compare them, look at this cluster. Look at this cluster, look at this one. Look at this one over here. is the entire region. So it's very, it's visually poverty and mortality from diabetes seems to be associated. Areas which are poor have a high mortality due to diabetes. But what we want to do is a statistical test. So let us go. No, first we have to create the category. So save category. So it was, let me call it PCAT. So PCAT will take 4 values. And again, we want to convert it to 1 value in the same way as before. So let me go for PCAT 44. Now we just add a variable called SCOF. Again, it's assigned. So just check. So it's 1001. Yeah, so it is 4334. So the assignment is correct. If you want, you can save it. So I don't need these maps. So let me close them. What I'll do first is I'll create unique values map for both diabetes for both diabetes and just 1 second. So you can see over here. Sorry, actually I made a mistake. I was showing it for, I have to show the bivariate, but I've shown you the example for the non-co-location. Sorry, I showed you. I'm showing you for this actually. Co-location joint count statistics. Anyway, since I've done part of it, let me explain this, then I'll go back to the map. So basically you understand how to create you have got a continuous variable, how you convert it to binary. And the objective is to find out whether you have co-locations. So as I said that you can have 2 situations. One is co-location. So both diabetes and poverty happens in the same location. If the area is poor, mortality is high. If the area is not poor, then mortality is low. Or you can have a situation non-co-location. So if it is an urban area, that means it's not a rural area. Or we can say like this, X and Z are variables which are mutually exclusive. So let me think of it. So you can see whether it is So for instance, whether we are trying to classify an area as a urban area or as a rural area. So we have one variable is defined as urban. So urban is equal to 1 if it is an urban area, and Z is another variable which is rural. So if rural is 1, it means that area is rural. So obviously if a area is urban, it cannot be a rural. It will be something like this. This is your X and this is your Z. So if it is an urban area, this has to be 0. On the other hand, if it is a rural area, this has to be 1. If we cannot have, these situations are not possible. These are not possible. You have defined X and Z in such a way that X equal to 1 implies Z equal to 0 and vice versa. So okay. So in case of co-location, okay, let me save this file. Then I can come back. Let me open the Chicago Common Pop. So let me see, we have got two variables. One is pop plus and the other is pop negative. So these are where population has increased. These are where population has come down. And you can see that they are mutually exclusive. If you have got 0 over here, this is 1. X is 1 over here. Z is 0. Okay. So we go to space, bivariate local join. Oh, I forgot the weights again. So tools, weight manager, we have to load it. Hopefully it's there. Yes. Space, I go to bivariate local join, pop plus and pop nick. And the weight should be here. So again, you can see that you have got clusters. So slightly more clusters, and you can again change the randomization to see whether there's any effect. So it's better if we keep the unique value maps. So just let us look at this. So you can see that this is a map where pop plus, which is X, is high, that is 1. And look at the clusters over here. So what is the value of Z, which is pop neck? It is 0. Okay. So if X is equal to 1, Z is equal to, of the neighbors, is equal to 0. Let's look at this one. Again, we can see that, look, if this is X is 1, the surrounding areas, this is the cluster. These are not part of the cluster. This part of the cluster is POPNEC is, that is Z, is equal to 0. So, I mean, those who are undergrad students, I mean, as I've said again, they will find this class a little bit difficult. PhD also, you may find it difficult, but just keep in mind that we don't really, generally, we don't use categorical variables or binary variables in spatial analysis, but sometimes we do have to use spatial binary variables. In such cases, only this joint statistics will become important. So it may not be very clear, but if you think about it, it will take some time to understand. The class is not the best place to understand it. You'll gradually understand the intuition behind this. With co-location, what we have is, remember, this was the first situation, that both the variables can take the same value. So you have high poverty levels, you have high diabetes deaths. So in this case, you have to use spatial weights, and this is the Anselm and Lee statistics. Okay, so I'll just show this to you. So this was the common area. So I've already saved the files. I don't have to do much about it. I just open the weight file, which also I have created. This is the co-location joint count. So I choose SPOF and SDIAP. The weight is already there. And we can see that there's a clusters, 2 clusters. So the association between poverty and diabetes was clear from the unique value maps. And here we see that there are also spatial, some very limited amount of spatial spillovers. In these 2 blocks, the surrounding area also has, so if you take high values of poverty and diabetic mortality, the surrounding area also is similar with respect to poverty levels and diabetes. So we have only 3 clusters over here out of 77. Let me delete the variables. So SPOV and SDIAP I'm deleting. Over here, DCAT and PCAT also I'm deleting. So let me save it. I've got back my original form. So lastly, I look at quantile LISA for a categorical variable. So although it's for categorical variable, we can also apply it to a continuous variable. What we simply have to do is, we have to convert the continuous variable into 4 categories. So first we go to map, quantile map. We have got 4 categories. And now we are going to use, let's say we are going to look at poverty. POV 50p. So this is the map. And we save the category. PCAT4. Then we go to space. There's a multivariate quantile Lisa. So this is 4. We make it both of them 4. So we keep these default names. So needed for diabetes. PCAT. Go to space, multivariate quantile. PCAT is already there. Now bring in DCAT. So we see that again we have a cluster at the same locations. So this indicates clusters where poverty levels are also high and where the diabetic mortality is high, not only in a particular district but in the surrounding areas. So remember, we are not taking the original district, we are only identifying the neighbors. Which of the neighbors have similar characteristics in terms of poverty and mortality rates. So I think today's discussion was quite difficult and perhaps not so interesting. So I'll stop at this point. Don't worry, as I've said again, and repeat it again, don't worry if you can't understand it. Go through the material which we will supply. If you do have to work with categorical variables, it is always better to read it up. Otherwise, you can safely ignore this discussion. In the next class on Friday, I'm going to we are going to continue the discussion of regressions. See, what happens is, the basic assumption was of spatial homogeneity. Okay. So the variable that we are observing, let us say stunting, that can vary across regions, but the relation between stunting and child marriage, for instance, is assumed to be same across all areas. And this is a pretty strong assumption. One way of relaxing this is through the GWR, which I've discussed. But as you know, GWR cannot be done in Geoda. And sometimes we also don't need to do it. We don't need to go to such complex models. What we have is the population may be divided, or the area that we are studying may be divided into 2 or 3 regions. We call them spatial regimes. So for instance, the relation between poverty and crime may vary between rural and urban areas. The relation between population density and crime can be positive in an urban area. It can be negative in a rural area. So in such cases, you have to use a technique called the spatial regimes. You have to first start with an exploratory analysis, and then you can add this to your regression. So this is something if you have done, I don't think it has been covered in your DSC econometrics, but this is equivalent to you have a time series data and you feel that there has been a structural break. So we apply Chow tests. So the spatial regimes are equivalent to the structural stability of data, and we test them using Chow tests. So anyway, I'm going on for a long time. I think you can leave now, but I would like two people to stay behind. One is Shukarna and the other is Moyuk, please. I think both of you were facing some problem.